Over the past few years, I've done several videos on the law of distribution. These videos came about because of my response to Presh Talwalkar's video on order of operations, and my point has consistently been that distribution is way more powerful than following the rules of PEMDAS. In fact, as I've mentioned elsewhere, the rules of PEMDAS aren't even accurate, especially when you're given the order that you must solve everything from left to right. The fact is, distribution is amazing. If you understand what you're doing with distribution, it will make a lot of complex mathematics far simpler to do, especially if you're looking for mental shortcuts to simplify things. Let's face it, we all want to do things easier, and if there's an easier method of doing something, you're less likely to make errors on it too. Furthermore, finding alternative ways of doing mathematics allows you to check your results, because you can solve them in two different ways and get the same answer. So let's discuss the beauty of distribution. First, let's answer a simple question. Look at the following equation. How can you solve it? 5 parentheses 2. Now don't be too quick on this. Obviously, you can just multiply 5 and 2 together and get 10. But that ignores the actual question. How? How is it that you can treat parentheses as if they are multiplication there? Parentheses are not multiplication. They are grouping symbols. So what justifies you treating them as if they are multiplication here? The answer is the law of distribution is the reason you can treat them as multiplication. To show why, first we need to ask just what is distribution? Well, distribution is one of the fundamental laws of mathematics, and it's the law that governs what happens when you need to do multiplication and addition at the same time. That is, it's when we need to distribute multiplication through addition. It is demonstrated in the following equation. A parentheses b plus c end parentheses equals ab plus ac. Now, of most interest is the fact that when you look at this formula, there is no multiplication operation shown on the left-hand side of the equation. There is an a followed immediately by a grouping of b plus c. And what this says is that we can treat a parentheses b plus c end parentheses as if we were to multiply a times b and a times c and then add them together. Now, it's easy enough to test that out if we just substitute in some values. Let's just look at a equals 3, b equals 4, and c equals 9. If we substitute those values in, we get the following. 3 parentheses 4 plus 9 end parentheses equals 3 times 4 plus 3 times 9. So what this is telling us is that if we want to solve 3 parentheses 4 plus 9 end parentheses, we do so by multiplying 3 times 4 and 3 times 9, and then summing those two products together. That's easy enough. 3 times 4 is 12, and 3 times 9 is 27. 12 plus 27 is 39. This means the law of distribution says that 3 parentheses 4 plus 9 end parentheses is simply another way of saying 39. So how does this give us the ability to treat parentheses as multiplication? Because we can make a simple observation. When we look at 3 parentheses 4 plus 9 end parentheses, there's nothing forbidding us from adding 4 plus 9 together before we do anything else. And we can see that 4 plus 9 sum together to give us 13. Now, because we know that the entire equation before we sum 4 plus 9 is equal to 39, this means that we are now left with the following equation. 3 parentheses 13 end parentheses equals 39. And given this, it's very simple to see that the relationship between 3 and 13 that results in 39 is if we multiply 13 by 3. Since we know that 3 parentheses 13 end parentheses must equal 39, then we can implicitly use the parentheses as multiplication here. That is what justifies us saying that parentheses are implied multiplication. It's because it's actually distribution, and distribution involves both addition and multiplication, both of which have to be completed before distribution is considered to have been completed. And the beauty of the law of distribution is that it shows us that it doesn't matter whether we do the multiplication first or the addition first. We can do either one and still be assured of the correct final result so long as both are completed before we do anything else. Again, this implicit multiplication is proven to be useful only because we went through the step of distribution in order to prove it. Now that it has been proved, we can use it without bothering to go through the complex proof each time. Pretty cool. But here's the problem when we come to more complex equations. It is mostly evident in equations involving division because, as I've mentioned in other videos, division is not communicative nor associative. So those equations can be a bit more tricky. Equations like, I don't know, 60 divided by 5, open parentheses, 7 minus 5, close parentheses. I don't know why that one seems so relevant. Must be a message from Nostradamus or something. Anyway, as I've discussed many times in other videos, proponents of PEMDAS supremacy argue that we must first do the parentheses. Now, what does do the parentheses even mean? It certainly doesn't include multiplication like is done in distribution, because they specifically say we cannot do that step until we are on the multiplication step. So that means that the proponents of PEMDAS is treating the parentheses solely as a grouping symbol here. That is why they will say, first subtract the 5 from the 7 and get 60 divided by 5 parentheses 2 end parentheses. Then they will argue we do the multiplication and division on the same step. So we must do it left to right, giving us 60 divided by 5, or 12, and then multiplying that by 2 to give us the answer of 24. But here's the problem. After they divide 60 by 5 and get 12, what justifies them treating 12 parentheses 2 end parentheses as if it's multiplication? Now, I've already shown you earlier that this works because of distribution, but distribution requires one to distribute multiplication through addition. That is, we must do both steps in order for the problem to be finished. That means when we started way back at 60 divided by 5 parentheses 7 minus 5 end parentheses, if we add our negative 5 to 7 to get 2, we must immediately do the multiplication as well. That's what distribution requires. 5 times 2 equals 10. That gives us 60 divided by 10, which is equal to 6. The proponents of PEMDAS have inadvertently committed the logical fallacy of ambiguity. That is a logical fallacy, whereby a term has a different meaning, and the meaning of that term is changed from one meaning to the other during the course of a logical argument. An example is the fact that sides of rivers are banks, and banks are where we store money, therefore money is stored on the sides of rivers. Now clearly we know that the word bank has changed meaning in that example. What is less clear is that the proponents of PEMDAS have changed how the parentheses are being used. In the first step, parentheses are merely grouping functions. That's their only role in the P in PEMDAS. We do parentheses first because those are the things that have been grouped for priority's sake. But the parentheses are still there after we convert 7 minus 5 to 2, and without any justification, the proponents of PEMDAS changes the meaning of the parentheses from a grouping symbol to now suddenly just being implied multiplication, completely ignoring the fact that you only get implied multiplication from distribution. But I've already gone over this ground many times, so I won't do so further now. What I really want to show you now is how much easier mathematics can be if you ignore the rules of PEMDAS and only use them when they actually matter. Let's look at an example. How would you solve the following? 3 times 7 plus 4 times 7 plus 8 times 7 plus 1 times 7 plus 2 times 7 equals x. Now the rules of PEMDAS are strict. You have to do the multiplication first, then the addition. That means the only way you can solve this according to PEMDAS is as follows. 3 times 7 equals 21. 4 times 7 equals 28. 8 times 7 equals 56. 1 times 7 equals 7. And 2 times 7 equals 14. Now you add all that up. 21 plus 28 is 49. 49 plus 56 is 105. 105 plus 7 is 112. And 112 plus 14 is 126. Now, I don't know about you, but that was a lot of work, especially when you can clearly see that each one of these was multiplied by 7. You know what you can do when every term is multiplied by the same factor? That's right, it's kind of given away by me emphasizing the word factor. You just do the reverse of distribution, which is factorization. You factor it out. Our equation can be rewritten as follows. 7 parentheses 3 plus 4 plus 8 plus 1 plus 2 end parentheses. And now we can use the fact that we already mentioned. When doing distribution, you can do either the addition or the multiplication first. It doesn't matter which. So that means we can simply add the numbers in the parentheses together, and this can even be done in your head. Just glancing at it, I see the 8 and the 2. That gives us 10. 10's a nice number to hold. The remaining numbers are 3 plus 4 plus 1. That's the same thing as 4 plus 4, which is 8, so we have 18 total. I did all that in my head just by glancing at this. So by leveraging distribution in reverse, that is factoring, we factored the original equation and simplified it. All that jazz really boils down to 7 times 18. But you know what? I don't like multiplying by 18. I'd rather multiply by 20 because I can do that instantly in my head. 7 times 20 is 140. I know that because 7 times 2 is easy to solve as 14 and 20 is just 10 times 2. You combine those together, 140. So boom, in my head, 7 times 20 is way easier to solve than 7 times 18. Of course, 7 times 20 isn't the correct answer. So there's still a problem. But you know what will let me multiply by 20 while still multiplying the 18 we actually need? Well, knowing that 20 minus 2 is the same thing as 18. That's right, I can convert 7 parentheses 18 end parentheses into 7 parentheses 20 minus 2 end parentheses. And now when I distribute, I know I will be getting the 140 that's so easy to calculate, and I just need to subtract 14 from that. 140 minus 14 is easy to solve in my head to give me 126. The same answer as before. But here's the thing, in my opinion, this is way easier to do, and it gives the correct answer, and yet not a single step I did is permitted by PEMDAS. Oh, and it gets better. What if we had this instead? 3 times 4 plus 5 times 9 plus 2 times 4 plus 6 times 9. How would you solve it? Again, PEMDAS requires a specific way of doing it. I don't want to do it that way. We have 2 numbers that are multiplied by 4, and we have 2 numbers that are multiplied by 9. So what if we did this? 4 parentheses 3 plus 2 end parentheses plus 9 parentheses 5 plus 6 end parentheses. Well, now that gives us 4 parentheses 5 plus 9 parentheses 11. And that's already easy to answer since it's just 20 plus 99 or 119. But I can do other manipulations too. Look at this point. Once I convert 4 parentheses 3 plus 2 into 4 parentheses 5, in the first term, I can immediately see that there is a 5 inside the 9 parentheses 5 plus 6 as well. So because I don't care about PEMDAS here, let's pull that 5 out. What I mean by that? Simple. We distribute the 9 through the 5 plus 6, and we get 9 parentheses 5 end parentheses added to 9 parentheses 6 end parentheses. And this means for the entire equation, we now have 4 parentheses 5 end parentheses plus 9 parentheses 5 end parentheses plus 9 parentheses 6 end parentheses. And again, because we know from distribution that since 5 can be factored out of 4 times 5 and 9 times 5, then we can add those other numbers together. The 4 parentheses 5 end parentheses plus 9 parentheses 5 end parentheses is really the same thing as 13 parentheses 5 end parentheses. That means that we can convert this whole thing into 13 parentheses 5 end parentheses plus 9 parentheses 6 end parentheses. And if you don't believe me, simply calculate. 13 times 5 is 65, and 9 times 6 is 54. Add those together, and we're looking at 119. That's the same number as before. What are the odds? But we can go even further. Suppose that I don't like multiplying by 13. And to be honest, I really don't like multiplying by 13. So when we're at 13 parentheses 5 end parentheses plus 9 parentheses 6 end parentheses, I can leverage the fact that distribution lets me treat parentheses as implicit multiplication to reverse the 13 and 5 and treat it as 5 factored out of 13. Now that I've done that, I'm deciding to spell 13 as 10 plus 3, because I can. In other words, because I know how distribution works, if I don't want to multiply a number by 13, I can simply change 13 parentheses 5 end parentheses into 5 parentheses 10 plus 3 end parentheses. And I know this is valid because distribution lets me do this. So now I have 5 parentheses 10 plus 3 end parentheses plus 9 parentheses 6 end parentheses. And you know what? That plus 3 there at the end gives me an idea. 9 parentheses 6 is, 6 is just 3 plus 3. So I can convert this whole equation into 5 parentheses 10 plus 3 end parentheses plus 9 parentheses 3 plus 3 end parentheses. Now I have 5 times 10, which is dead simple. That's 50. What's left after that? We still have the 5 parentheses 3 plus 9 parentheses 3 plus 9 parentheses 3 again. And that's just 5 plus 18 parentheses 3, or 23 sets of 3s. So again, now we've converted this whole equation into 50 plus 23 parentheses 3 end parentheses. Again, I don't like 23 as a number. It's too big to deal with simply in my head. But 23 is just 20 plus 3. So I can convert this once again. I keep that 50 that I already solved, and now I have 20 parentheses 3 plus 3 parentheses 3. So that's 50 plus 20 times 3, which is 60, and 50 plus 60 is 110. And we're adding that to our leftover 3 plus 3 parentheses 3 end parentheses, which is 9. So 110 plus 9 is, wait, who would have seen this coming? That's the same 119 we've already solved before. Sure, these ending steps were a convoluted process to get there. But the point is that even giving myself these arbitrary decisions of what mathematics I don't feel like doing, I got the right answer. That is the power of distribution. In fact, that's the secret power that I wish more teachers would teach about mathematics. There are always certain numbers that are more difficult to calculate with. And as I've just shown, using the power of distribution to rewrite those numbers into something your brain can handle far easier makes mathematics a whole lot simpler. And for my final point, I'm going to be a bit pedantic here. I'm going to go ahead and go for the jugular. I've had dozens of fans of PEMDAS tell me that I don't know what I'm talking about, or I don't even understand basic mathematics. Can any of you guys do what I just did? I can answer that for you right now. No, you can't. Why? Because every step I did violates the rules of PEMDAS that you hold so sacred. And yet, I dare say, any reasonable person who is looking at my ability to transform equations into whatever numbers I feel like and still get the correct answer at the end ought to conclude that this proves I have a far better understanding of mathematics than the person who can just quote a rule that a teacher once dictated without providing any reasons for why that rule should even exist. PEMDAS is a method, and yes, it usually gets the right answer. In fact, you could even update PEMDAS to include distribution and improve it a little bit. Of course, it would no longer be PEMDAS at that point, but de PEMDAS or something like that. The point is, there is more wrong with PEMDAS than just the fact that it's missing so many operations that you can do in mathematics, like trigonometric functions or factorials or the like. What's worse than what is missing from PEMDAS is the very rigid claims of how you must do mathematics that permeates the teaching of that rule. This rule is taught by people with no understanding of mathematics, and then it's used to browbeat people who do understand mathematics into conformity. PEMDAS proponents, unwittingly as it may be, are teaching people a skewed view of mathematics. Worst of all, these people have added the arrogance of thinking that because they can quote a rule without knowing any of the context for why the rule was even there, that they are now qualified to correct those who actually understand mathematics and who know why the very rule they hold so sacred is fundamentally broken. But that's just a theory, a math theory. And with that, I hope you all have a wonderful day. Peace out.